chi-square distribution is the sum of the squares of k-standard normal distributions. It approaches a normal distribution for punctualities or k. As you can see from the graph, the degrees of freedom in a chi-square is strongly affected state. Chi-square tests have multiple uses. They can be used to assess the normality of a population, test how the problem says about a population proportion or variances, check dependency between multiple groups, and evaluate the rate of change over several periods. We'll be focusing on goodness of fit. Goodness of fit is a hypothesis test that has a null hypothesis that are proposed relevance of set of data. The test assumes that observations are approximately normally distributed and independent of each other. When grouping the observations, groups are formed from expected value in the group. It's possible to have a group with zero observations. The chi-square test statistic is the sum of the squares of the deviations from the expected number of observations in each group, weighted by the reciprocal of the expected number of observations in that group. In general, the number of degrees of freedom is the number of groups minus 1. However, if the parameters of the model are fitted from the data, then the degrees of freedom are further reduced by the number of parameters.
Now we're going to do an example. Group 6 auto insurance have claims that fall into the following 4 categories with the given probabilities and number of accidents for the current year. Test the null hypothesis that the probability of each claim amount for the current year are the same as the given probabilities. To do this, we're going to A, create a chi-square table and determine the degrees of freedom. B, determine the result of the chi-square test at the 0.95, 0.50, 0.10, and 0.01 significant levels. Here are the solutions. For part A, create the chi-square table. We simply write out the information from the first table and calculate the expected value in the chi-square test. With the expected value, you calculate it by taking the given probability times the total amount of claims. For each row, we do that and we get our current value. To calculate the chi-squared, we do the expected value minus observation squared divided by the expected value. As you can see, we have those values as well, and then you sum them up to get 5.5 is equal to our chi-squared. To determine the degrees of freedom, you take your number of rows, which is 4, minus 1, minus 0, because we're not estimating any parameters. For us, we get a degrees of freedom equal to 3. Now on to part B. Determine the results of the chi-square test at the 0.95, 0.50, 0.10, and 0.01 significant level. To do this, we use our calculated chi-square and compare it to the chi-square on the table. If your calculated chi-square is greater than the chi-square on the table, you reject the null hypothesis. If your calculated chi-square is less than the chi-square on the table, you fail to reject the null hypothesis. Moving to our table, we have degrees of freedom of 3 and a chi-square of 5.5. It lies right in between where the red mark is. So, since 5.5 is greater than everything from a 0.1 significant level, we can reject H9. And since 5.5 is less than a 0.9 significant level, we can fail to reject H9.
Alright, so here's our second example. This is similar to one of the SOA problems we worked. You're given the following sample of 25 claims. There they are. And you want to test the hypothesis that claims follow a continuous distribution with the following percentiles. These are them. You want to group the data using the largest number of groups such that the expected number of claims in each group is at least 5. And we split this up into 3 parts. So part A asks you to calculate the chi-squared goodness of fit statistic. So for the given intervals, we have that the expected number of claims in each group is, so from 0 to 300, you can look at your CDF. You know that your probability of being in that interval based on the hypothesis, and we're calculating expected, so is 0.2. So 25 times 0.2 is 5. Do the same thing for the interval from 300 to 600. You take f of 600 minus f of 300 to get your probability of being in that interval. Multiply it by the total number of observations, 25. You get 3.75. So on with these, you get 2.5, 5 expected claims in that interval, and 6.25 expected claims in that interval, and 2.5 expected claims greater than 4,800, based on the hypothesis. So to get our total of expected claims in each group above 5, you group these two together and these two together because you got to get that 2.5 up. So then, like LaShonda said, it's pretty convenient to make a table for these problems. So we have our new interval, 0 to 300, 300 to 1200, that's grouped, and the 2400 plus is our other group 20. The expected number of claims in each of these intervals, the first one's 5, obviously, the second one's 6.25, you just add up these two. Third one's 5, and the last one is these two added together. The observed number of claims, you just go right here, you just count. So 1, 2, 3, 4, 4, 0 to 300, 1, 2, 3, 312, 1, 2, 3, 4, 5, 6. It's just pretty simple. The chi-squared statistic, like we said, is the sum of your expected minus observed squared over the expected. Each of these is for each interval, so you get 5 minus 4 squared over 5, 0.2, so on, and you sum those to get your chi-squared statistic, and you get 0.99. In the second part of the problem, you're asked to recalculate the chi-squared test statistic with your data truncated at 300. So I denoted this as these are your new CDFs with the truncation in effect. So f of 300t would be 0. With your new interval, you just take the original probability that you're in that interval. So from 300 to 600, you have a 0.15 chance, and it's like a conditional probability. You just divide by the probability that your value is greater than 300, so 0.8. That gives you 0.1875. Then you do the same thing as before, but instead of multiplying by 25, you multiply by 21 because these 1, 2, 3, 4 values are thrown out. So your expected number of claims in that interval now with the data truncated at 300 is 3.9375. I'm going to zoom this thing out. Okay. Better? Alright. You do the same thing for this. Your new interval with the truncation from 600 to 1200 is your original 600 to 1200 interval probability divided by the probability that you're above 300 to start with, 0.125. You multiply that by 21, and you get your expected number in the new interval from 600 to 1200 is 2.625. Do that with the rest of these. We're still grouping it in the largest number of groups, so each group contains at least 5 observations. So we're going to group the first 2 intervals and the last 2 intervals. So here's what our new table looks like. We have our hypothesized expectation, these 2 added together, this one, and that's these 2 added together. Our observed, again, you just go back to the data and just count how many's in that interval. So 6, 4, 11. You total these up. A good way to check if you're doing something wrong is if these don't total up to the same number, you messed up. So these both total to 21. You get your chi-squared statistic the same way as before. You add it up and get this as an answer. So finally, part C asks you to recalculate the test statistic with your data sensor at 1,000. So you just do the same thing as before, but instead of censoring, truncation, anything, you just throw it out. Censoring, if it's above 1,000, it becomes 1,000. So this is 1,000, all these become 1,000. So you're still going to have 25 observations. Your probability that you're from 0 to 300 is still 0.2. This is the same. Probability from 0 to 600 is 0.35. Probability that you're under 1,000 is 1 because you cannot be above 1,000. Censored at 1,000. So your probability that a randomly chosen observation is in the interval from 0 to 300 is 0.2. Therefore, your expected number of claims in that interval is 0.2 times 25, that's 5. From 300 to 600, 0.35 minus 0.2, your probability of being in that interval is 0.15. So you multiply that by 25, and then 3.75 is your expected number of claims in that interval. Finally, you can just look at this. From probability of being from 600 to 1,000 is 1 minus the probability of being from 0 to 600. That's 0.65. So you multiply 0.65 by 25, you get 16.25. So we still need our intervals, the expected number of claims in each interval greater than 5. Group the first 2. Here's what our new table looks like. The totals go to 25, which is good. Then you calculate the test statistic. Sum these up, 0.367, and you're done.
All right, so for our last example problem, this presentation, we're going to do the SOA problem number 47, which has to do with fitting to a specific distribution the data that you're given. So the problem is as below. You're given claim frequency data over a period of a year, and they give you 0, 1, 2, 3, or 4 plus claims with a certain number of observed number of days for each. And they ask you to fit a Poisson distribution to the data using MLE, and then regrouping it and applying chi-square goodness of fit test to check whether the claims follow a Poisson distribution and determine that result. So the first thing you want to go ahead and do is determine the maximum likelihood estimator. So one shortcut is knowing that the Poisson distribution with MLE, the MLE is just the sample mean. So what you could do is just calculate the sample mean, and that's your lambda. But I'm going to go through the process of calculating MLE just as a review in case it comes up. So what you do first is you multiply all the individual probabilities that each event occurs. So it's f of 0, which occurs 50 times, f1 122 times, and so on. And then with the Poisson distribution, you get the individual probabilities, which is lambda to the k, where k is the number in the parentheses, multiplied by e to the negative lambda divided by k factorial. It simplifies down to e to the negative 365 lambda times lambda to the 600 divided by 2 to the 101 power times 6 to the 92 power. 92nd power. And what you want to do next is take the natural log of that function, and it gets you to that. And then after that, you want to take the derivative and set it equal to 0 to find where what the MLE is. So you get 600 over 365 in both cases, which is around 1.6438. All right, and so the next thing it asks you to do is regroup the data into 4 groups, 0, 1, 2, and 3 plus. So we'll create a table again like in the previous examples. And so the probability in each case is you take it from the Poisson distribution that you, with lambda that you just calculated. So it's 0.19324, 0.31765, and so on. And the last one is actually not f of 3 for that lambda because you need the probability to add to 1. So what you actually do is just 1 minus the 3 individual probabilities that you found earlier. And you calculate the expected number of days with that number of claims, and you have your observed, and then you want to calculate your chi-squared. And so your chi-squared, as they mentioned, is the expected minus the observed squared divided by the expected. But if you reverse that, that's okay as well because you're squaring it so it comes out even either way. So you input the numbers that you get from here. So you have 50 minus 70.53, and square that and then divide by the 7.53 for each row, and you get these numbers, and then it should sum to 7.56 approximately. So with that number, then you want to calculate the number of degrees of freedom to check the table. So what we have is we have 4 rows of data, and then you subtract the one estimated parameter based on Poisson, and then you subtract an arbitrary 1, and you get 2 for your number of degrees of freedom. And then with 2 as your degrees of freedom and 7.56 in your chi-square statistic, you go to your table, and so you see here we'll go to 2, and then 7.56 is approximately right here. So you would reject everything to the left. So you reject at you reject at a significance level of 0.025, but you would fail to reject at 0.01, which is answer choice C.